You are entering the Nillyverse with your hosts Gustavo and Rodney Perry. This episode has been brought to you by the Society of Namecoin. No. Hello, Rodney. This is our last episode of the year, maybe for a little while.
Unbelievable. Yeah, it's been a good run.
We've come full circle back to our favorite pop, Lawrence Krauss. Remember our critique on A Universe from Nothing. We can now look at where higher dimensions might lie and how we might experience them. And so Krauss is going to be sharing his thoughts on string theory with us on our Hop on Pop session right now. Let's just jump right into that.
Okay.
There was a host of new elementary particles being discovered, and it just seemed like chaos. And more than that, the theories that people began to develop to try to explain that were chaotic. They produced nonsense. They produced infinities. And it was recognized that one way around it was to assume that elementary particles themselves were maybe not particles, but at some small scale behaved kind of like strings. Because if that was the case, you could tame those mathematical infinities, but not tame them in 4 dimensions. It turned out the only way you could tame them is if there were a few extra dimensions, not 1, not 2, but 22 extra dimensions. And I find it fascinating that physicists were so terrified by these infinities that even in the 1960s, they began to take the idea of 22 extra dimensions seriously.
Real extra dimensions,
Real.
not mathematical metaphors.
Well, often mathematical metaphor becomes real, and the question is, which is which, and that's what makes it into physics, and we want to find out. But they were willing to believe they were real and ultimately might have physical effects. That ended in the 1970s when we, in fact, came up with a different theory that happened to explain all those experiments, get rid of the infinities, and it was beautiful. But it was revitalized in the 1980s when it was discovered that that same theory that had been thrown out actually naturally produced something that looked very much like gravity. Now, the big problem of the 20th century and the 21st century, perhaps, is that gravity and quantum mechanics don't mix. They don't work together. General relativity and quantum mechanics just don't work. But here was a quantum theory that somehow had gravity embedded in it, apparently. So potentially this was a quantum theory of gravity. And when that was discovered in 1984, that's when everything went wild and tons of physicists began to think seriously about these extra dimensions. And the question is, where are they? Well, if we don't see them, maybe they're very, very small. That was the idea for much of the 20th century. Maybe they're curled up into such a small scale that we can't measure them.
Compactified.
Compactified is the word. The question is why, and the answer is we don't know. And so that's been part of the issue, but it turns out that more recently, people have begun to consider the possibility that maybe there are other ways to hide those extra dimensions that make them more interesting. Maybe they could actually be large. And part of the reason trying to understand that was that one of the big mysteries in science is that gravity is much, much weaker than the normal rest of the forces in nature. It may not feel like it to you when you wake up in the morning and try and get out of bed. But gravity is by far weaker than the other forces in nature. It's a famous example. Go up to the top of a building, throw a friend off or an enemy off. It takes gravity all that distance, 200 feet, to get them down to the ground. But what stops them in the end? Electricity and magnetism, because it's the electric forces between the atoms in your hand and the floor that stop you. Most of it's empty space, it's just force. You don't even leave a dent in the concrete. So electricity and magnetism stop you in a fraction of an inch. Gravity accelerates you all the way down. Why is gravity so weak? Maybe it's weak because some of it's leaking out into extra dimensions. So if you and I are constrained to live in our 3-dimensional space and 1 dimension of time, but somehow gravity can probe those extra dimensions, then maybe those extra dimensions could be large, and you could explain the weakness of gravity. The final interesting aspect of these large extra dimensions is if they're large enough, maybe we can do experiments at high enough energy so when we bang things together, some of that energy will leak off via gravity into those extra dimensions, and we might actually experimentally probe it so this stops being metaphysics and becomes physics.
But do you think that's likely?
I wouldn't bet on it. I think it smells wrong, but it's certainly fun to work with.
That's great. I didn't know you did smell.
Yeah, hey, it might be a good segue into what you have to say later on. But he really does have a flair, right, for describing what's going on with extra dimensions and such, and just like sort of storytelling in general. But he does also, like with this video, sort of share with us that there is lack of consensus with what's going on. Strings and extra dimensions tame the infinities falling out of existing theoretical structures. He cites why this explanation is appealing. It's like one way to explain why the force of gravity is much smaller than, say, the electromagnetic force, right, is that gravity leaks out into extra dimensions. But there is still no consensus about where to look for them, right? This leaking can actually, he didn't say this, but happen on the large scale and on the small scale equally. So the problem still exists. Why are we now switching from looking at very small pactified dimensions to instead looking at the very, very large dimensions? Right. Right? It's just because maybe we've hit a brick wall, right, with the small. Right. And so, well, let's try something else. Let's try the very large. So Robert Kuhn, the interviewer here, at the end asks Krauss if it's likely these higher dimensions will be detected. And the funny way that he responds is that, sorry, by detected, we mean essentially, will it be real? Right. Will they be real?
Right. Will it be real?
And he says that it smells wrong. So, you know, it's funny because at the beginning, we couldn't show the entire length of this video, right? But at the beginning of the video, the very, very beginning, Robert Kuhn asks about like higher dimensions and about science, right? And whether they are scientific. And he goes, it's science, but maybe they're not real. This was a real head scratcher for me. I did want to sort of show our viewers sort of like that this is not like something that we're just putting into his mouth. He actually said these words, that it's science, what's going on with higher dimensions in string theory, but he doesn't believe that it's real.
That's right, he doesn't.
Crazy, huh? I think it's a matter of sort of like just they're grasping at straws. They want to extend the fabric of science, the explanatory fabric, right, that science provides, but they don't know how to do it, how to make that leap from where we are today to where science needs to go to explain the moment of the Big Bang, for instance, and if there is a before the Big Bang. I don't know, was there anything that you'd like to add about this video here?
Well, I think that he brought up, I've listened to him on other situations, you know, on other YouTube videos talking about string theory and so forth. And it's an interesting thing that he does. He says that physicists have been utterly fascinated with string theory. And even though it's never solved a problem and it's never been shown to be real, there's an other fascination. It's interesting for how we've been talking about it in terms of faith and so forth. Scientists would not be able to explain their fascination because they're not fascinated by the empirical here, which is an interesting kind of draw or leaning forward, as we say, into an area that's beyond rational understanding. And the other thing is that mathematics is so compelling. He mentions the earlier time of 22 dimensions. It's now down more to 10, depending on who you listen to, or 10 or 11 sometimes. But still, there's this notion, because it looks so good according to the math.
Yeah, it looks good on paper. It looks
really good. And so I think that's very telling and, you know, very interesting.
I don't know if he knows, which camp where to lean. You know, I think he's right in the middle, right? He wants to believe, but there's this part of him that's telling him, no, you need empirical evidence here, or else you're not a scientist anymore. You're not functioning in the capacity of a scientist.
And the leaking off notion about gravity is something that I don't have a subtle enough physics understanding to get. But the language of leaking off is very much the language of storytelling and images, not the language of science to me.
The leaking off does make sense. It's a valid explanation because, like, we understand that as something spreads in 2 dimensions, right? Like, say, a circle, right? The area of a circle proportional to the square of the radius. The area of a circle is pi r squared. But if you take that, the same size, like the same radius for a sphere, the volume of the sphere is 4/3 pi r cubed. So the volume increases far more rapidly than the area of something, to an extra order of magnitude, right? So that if gravity were sort of localized, right, and had to spread in all directions, the more it has to spread to further to other dimensions. So instead of a sphere, we had a 4-dimensional hypersphere or something like that. You can imagine that it would have to get weaker if it somehow had the power to spread into higher dimensions, but other forces did not for some reason. Now, there is no mechanism to explain why that would be, but if there was a reason somewhere down the road, right, like you could sort of point to and say, look, that's why gravity is weaker, right? Then yes, there is, it's due to this leaking into other dimensions. But hey, look, it's a great story that they're weaving for sure, and incredibly important exercise in logic and mathematics. But how much of it is real, right? And we need to make sure that as scientists, the scientific evidence, we make sure we limit it to what we've observed. And then when a scientist wants to share with us what his interpretation is of that evidence, then he has to make sure that he bolds the fact that this is now my interpretation and not what science is saying.
That's right.
The data is what we've observed, but now what we're doing is adding our interpretation of what this all means. Your interpretation can be correct, and it's perfectly good. We're human beings. We want to understand the why question. So it's good to ask yourself, well, what does the data mean, and to have responses for it, right, based on what you know. But you have to be honest in when you present this information to the people that don't have access or don't care to have access to the data. They just want the conclusion. What does this mean? Make sure that you tell them, like, listen, here's what the data is, and if you don't want to read that and you want to hear my interpretation, that's fine, but it's my interpretation of the data, and other people are interpreting the data differently. Interpretations are not scientific. It's backed up by evidence. Okay, so there's an alternative to how to visualize what's going on with unseen dimensions and how they can be permitted to exist as a matter more of convenience. Now, imagine a point in space, in empty space, and you're the observer looking on. So it's you and this point of space, and it's empty, right? We're in empty space. If you notice a uniform change in the relative position between you and the point, the theory of relativity says that the dynamics of what is being observed is equally describable from either the perspective that the point is moving relative to you, or that you are moving relative to the point.
Right.
That's what the theory of relativity says. Put it another way, physically speaking, both ways of seeing what's actually going on are equivalent and indistinguishable in empty space. There is no vantage point from which to say that it is the point or the observer which are moving.
That's right.
So, for this reason, concepts such as space and time are considered to be relative quantities. One might use the feeling of their body undergoing an acceleration as proof of their motion. Like, say you're in an elevator, you know, as soon as you start going down, it's like, whoop, you know, your stomach drops. You are feeling an acceleration. That gives you evidence to say that you are moving. And that's the proof of the motion in absolute space. But Einstein generalized his special theory of relativity, take into account the feeling of acceleration through space as being indistinguishable from force due to gravity. Force that does not necessarily depend on motion, but rather a changing field of masses around you. You can feel the change you have moving through space alternatively. So you're moving through space alternatively due to bodies moving around you. Moving gravitational field is felt by your body. Imagine yourself, if there was such a thing as absolute space, be stationary in absolute space, and these bodies moving around you actually make you feel as if like that you are moving. Of course, only very few of us have ever experienced life in deep space. Humans have backdrops of mountains, trees, and buildings, all of which we assume to be static because of how uniformly they maintain their separation between each other at any given time. If I'm in a car in the countryside or whatever, and I'm driving past like in a road parallel to like, say, a mountain range, I assume that it is me that is moving and not the mountains, right? Because all the mountains and the trees are staying relatively sort of evenly spaced apart, and I'm the one that's feeling the bumps along the road and all that. So I assume that it's me that's moving and not the mountain. It's only because of the backdrop that we have and these assumptions that we make in our heads about sort of this constancy of the separation between elements in that backdrop. When we perceive a change in our field of vision, even in the absence of forces felt on the body, it's reasonable to assume that we move and the mountain does not. Mountain is tethered to the earth. We take that as an assumption. The mountain is on the earth. However, if you were to look up at the sky for long enough, you can see the sun moving across. If we can understand intellectually how the world revolves to give us the appearance of a moving sun, so we understand that intellectually, but we still see it as the sun rising and setting.
That's right.
If we look up long enough, right, we could see the movement, or what appears to be the movement of the sun across the sky. We understand it intellectually that it's the other way around, right? That it's the Earth is revolving and giving us the appearance of the sun moving. But we still say that it's the sun that rises and sets, right? So which is true? Does it matter? For the purposes of making predictions about something like what is the position of the sun at time X, it simply doesn't matter which is true. And again, I'm going to bring up one of my favorite sort of philosophers of science or historians of science, Thomas Kuhn. In his book, The Structure of Scientific Revolutions, he points out that it's science. Science doesn't concern itself with truth. It concerns itself with solving problems. Right? Questions like that of what the position of the sun is at time t are what many scientists are asking at some level when they're doing their work. They're asking questions similar to that. What is the position of the sun at this time? If this is correct, then perhaps scientists can temporarily let go of what is real and instead look at the world as it presents itself before our very eyes. So let's go back to our point mass. Let's take the point mass some distance away from us in deep space. If I see movement in my field of view, I can either assume that the point moved to the right, my right, or I moved to the left. From my perspective, the point moving to the right or my moving to the left
is the same.
Is experienced the same way. Both describe the same phenomena, and we can measure the movement instead of with meters. Now here's something that I created. I call it a relative meter or a realm. A realm is, as I've defined it, is a meter as perceived from a meter away from the eye. And we define, like, say, something like a realm shell. A realm shell is it's like an imaginary shell, imaginary spherical surface created by spanning that 1 meter away from my eye. Okay, so if roughly my arm is about a meter in length, I were to hold a meter stick at the end, like on a stick, and right at the end, and what I did is I measured movements using this realm meter, or realm. That's the tool that I'm going to be using now to measure distances and velocities, right? So as the point moves across the field of vision of an observer, they can measure how far it moves along the realm shell or the realm meter and determine its realm velocity. Remember, realm velocity would mean the number of realms or relative meters spanned per unit time.
Per unit of time. Yep.
When dealing with point masses, we don't care about how far away they are from us, though the faster the realm velocity is registered, the greater the probability that the point mass is closer to us. So stars move very, very slowly across the sky because they're so far away from us. You can consider it like a point mass. And if I had a point mass close by, then if we're talking about in my field of vision, then they could be going in an absolute sense more slowly, but appear to be moving more quickly.
That's right.
According to my realm meter, because they're closer to me, right? Then it takes less time to span a realm when a point mass is close to me. Then up at the stars, if I point up my realm meter, it'd take a lot longer for the star to traverse the realm meter. But obviously the star is moving faster than the point mass. Why is this important? Why go through all this? Well, let's add a second point mass. So we have 2 point masses, such that the 2 point masses appear to be moving closer to each other. I can use a realm shell and a stopwatch to measure how quickly the masses are approaching one another using the laws of kinematics and a little math to make predictions about when and where they're to be expected to collide, for example. Of course, the particular questions asked by scientists are far more complicated than the simple example. But again, these are the kinds of questions that science is most effective at answering. So naturally, if we're able to simulate phenomenon, and remain faithful to all the relative proportions in real life, then we can draw the same conclusions as we did from measuring everything in real life. So computer simulations here, right, are employed nowadays to do exactly this for meteorological, cosmological, biological, chemical, and other complex physical processes. We use computers to simulate what's going on, where human calculations would otherwise be grossly inefficient or insufficient to model reality. Science accepts and, quite frankly, relies on the incredible power of today's supercomputers to solve these problems. All this to say that scientists shouldn't have an issue stripping away reality from phenomena in order to solve the problem of the day. So let's go back to our 2-point masses on a collision course with one another. An observer could see them moving towards each other due to their motion, or equivalently, instead of the two particles moving towards each other, the observer could see the same phenomenon pulling away from two static points, pulling away in a third dimension to the plane of motion. Granted that the further one moves away from the points, the slower the points will appear to be moving towards each other, right? The further and further I go, right, the slower it's going to change in my field of view to reproduce that uniform motion between the particles. But all that means is that simply that the observer would have to pull out in the third dimension at an accelerated rate to reproduce uniform motion of two particles.
Right.
All it means is I have to, slowly pull away and then start pulling away faster to reproduce that uniform motion. But I can reproduce it just by, instead of assuming that it's two particles moving closer to each other, one observer moving further away from the two particles. Those are equivalent.
Right.
Or they can be made equivalent.
That's right.
What value does this change of perspective afford scientists? Well, not much for this two-body problem. However, if we think of a 3, 4, or n-body problem, by that same reasoning, we can reduce the motion of n bodies in 3 dimensions from n equations with 10 variables. So you would need 3 positions. The particles are in x, y, and z. They have 3 velocities, vx, vy, vz. They have 3 accelerations, ax, ay, az, and maybe some time. Instead of having n particles in 3-dimensional space with 10 variables each, we can reduce all of that motion with one observer moving through an n+1 dimensional space, essentially. It's hard to visualize this, but you can totally visualize the two.
Right, you can do it too easily.
If you can do it too easily, it's not such a stretch to think you can do it with 3, with the observer moving into some 4th dimension, or with 5, with the observer moving in some 6th dimension. I don't propose to know what this space would look like, but I don't care. That's the point. I don't care what it looks like. The logic makes sense, and I can use that to my advantage as a scientist. For the purposes of analyzing the dynamics of the system at hand, it doesn't matter. What the higher dimensions look like doesn't matter. It's irrelevant. Books like Edwin Abbott's Flatland and Dewdney's The Planiverse, among others, are very imaginative in helping us to visualize higher dimensions, perhaps ill-suited to help us with our studies of what's going on in higher dimensions. It may very well be that the spatial dimensions beyond the 3 we have common experience of are better understood by letting go of what the eyes can perceive and just trusting our gut.
Okay.
Our moving through some n+1 dimensional space, and I know that because I'm moving, I can feel it. I can use that idea and Gestalt switch, instead of assuming that it's particles moving some box, right? I can reduce all of that to just one equation of one observer moving in some n+1 dimensional space.
Well, that's really interesting in the sense, one of the problems in searching for extra spatial dimensions is that the pops do a kind of direct projection of the three spatial dimensions onto whatever the higher dimensions are going to be. And it leads them in the wrong, distorts the trajectory of their research oftentimes by taking for granted that you can project. And oftentimes when they go to flatland, or like Michio Kaku goes to the fish in water, it's a very similar fish in water being taken out of the water is very similar to the flatlander in 2D being taken into 3. It's very similar. And the reason that seems so helpful in understanding is that you can do a direct projection from 2 to 3, water to air. You can do a direct projection. They're very similar. You can project directly. Oh, 2 dimensions. You see a sphere coming through your land is a circle. However, if you could make it 3, you would see that it's actually a sphere and so forth. And I think that they used flatland and the water as an explanatory, but I think it's a misdirection. That's a little bit, I think one of the things that you were just saying there is that you don't care about projecting directly your visual experience into the higher dimensions, but the realms description of higher dimensions actually lets you solve problems without being dependent on projecting the visual. Yeah, exactly. Which is interesting. Yeah, very interesting.
I don't care what the dimensions look like or if they're real even, right? They're useful fictions to solve problems.
They're useful. That's fascinating in a certain sense, very fascinating. To me, one of the things I was thinking as you were talking is that the realms is a sensibility that you have. Mm-hmm. And over these years that I've been working with you, I've come to understand that sensitivity. And it's not an easy sensitivity to pick up. However, it is a sensitivity that seems to be very consistent throughout as you present your k-optics. And now Relms isn't really a k-optic, although it partakes of a similar intellectual skill, you might say. Very interesting. And I think that would be unto itself a good lesson for Krauss to just hear this non-projective way of looking at higher dimensions. I think would really be helpful to it.
Really, the nut of it is stop trying to see higher dimensions and maybe try to reveal them in some other way. The section sort of speaks more about like how to do that, right, with through self-kenosis and such.
Yeah, I was really taken with that today. I learned something new about. So what we're presenting today are 2 very different but very coordinated ways of dealing with the same problem. Very interesting, I thought. I'll just do this quickly. We've been sort of going through this for a while now. I'll just go a little bit quickly just to present a little bit of another pathway toward other dimensions. As we've said, this last subsection in the text in our book, this last subsection is over 60 pages long. It's very complex, and it's probably the most intricate research that we presented through the whole book, because it brings in a lot of the things that we had done before. It comes from cognitive science, it comes from neurology, it comes from self-location studies. It's very difficult and complicated. So maybe I'll just, again, suggest that people read the book. Mm-hmm. Sometimes the complex discussion is not opaque if you read it. It's very complicated to do in a short oral form. So reading would be really good here. Again, this way of looking at extra dimensions, and I'm just going to go into it for a few minutes, begins with vision. And you dealt with that in terms of realms in a very interesting way. I'll just see how we go into this extra dimensions, always beginning with vision. So one of the things that, and I'll just go to some of the conclusions here so that we know where we're headed, and I won't have to take too long to get there. If I don't get all the way there, we'll know where we're going anyway. The way that we're looking at this aspect now is that extra dimensions can actually be physically seen. They can be seen with the eyes. And that what dimensions are perceived is dependent on where the self is located while looking. Mm-hmm. And the underlying notion here, the kind of leap one is asked to do here, is that the eyes must develop a skill for using the eyes as a tool. Using the eyes just like you would use a telescope, using the eyes just like you'd use a microscope or any other measuring device. So the notion is to use the eyes as a tool. And in understanding how to use the eyes as a tool, you'll see that at least two extra dimensions appear. And we call those the dimensions of the aesthetic, or the dimensions of the dynamic. That means a realm of color, light, and shape, and another realm of life that is based on motion, or basically on motion, on energy, on movement. So let me just do quickly. We'll go back to the 50s and 60s. This amazing man, the Canadian man, he was a neurosurgeon named Wilder Penfield. He spent his whole life trying to come up with a map, a kind of neurological map of the mind. Penfield's famous for this, coming up with this thing called the homunculus. And people may have heard of the homunculus. It comes from the Latin. It means a little guy, a little person. And the homunculus is this kind of distorted humanoid thing. And what he did was he created a sculpture. Well, I don't know if he did it as a sculpture, but he did it as a three-dimensional image of what a human would look like if the parts of the body expressed how much mental capacity is needed to use that part of the body. So it has really big head and really big hands. It's really a great image, and it's made him famous for a long time. He did a lot of studies, and one of the things that was interesting to him is he used to do these brain surgeries while people were awake. And he figured out that during these brain surgeries, he could use the patient as a subject in a study. And so he would stimulate various areas of the brain. And
what are you feeling right now?
Yeah, you probably couldn't do that. Ethics board of ethics wouldn't let them do that these days. But one of the things he discovered was that there seemed to be oftentimes two centers of activity in the brain. One would be trying to lift his hand, and the other would be stopping to lift his hand. And these two centers, he was looking for a single-centered brain, is what he was hoping for, kind of based on synapses and so forth. And he came up, but he finally concluded there had to be an extra dimension to the brain, a self that he called the watcher. The watcher was the human self within the human being. So this notion of the watcher, it was really essential to us, and it let us do a lot. We started to very literally, started looking very literally at this notion of the watcher. And I just mentioned a little bit of the science in terms of studies about self-location and so forth. The research has come to a basic consideration, or a basic acceptance, is that human beings experience their self as located in a single place within the body. Now that's no small notion. Human beings experience themselves as located. We've seen that in recent years, there has been a lot of discussion, experiment, and so forth that has concluded that there are really three neurocenters within the body, one in the head, one in the heart, one in the stomach. The stomach has been made very popular by this book, The Second Brain, that has come out. And what it has shown is that there are three independent neurological centers within the body. And when you look at the self-location studies from around the world, you see that there's an exact correlation between how people experience themselves to be located and those three neurological centers. So especially people in the West almost always locate themselves in their head. Sometimes during very different states of mind or different times, they'll locate the self in the heart, and sometimes they'll locate themselves in the stomach. In Asia, especially Japan, there's an age-old tradition of the self actually being located in the stomach called the hara. So the research we're looking at is that we have a watcher within ourselves. That watcher is located behind the eyes and the head, and I say behind the eyes in the chest, behind the eyes in the stomach, and that watcher can use the eyes, and when they use the eyes, they see different things. And our sort of insight, our kind of radical proposal is that these three locations actually are perceiving three different dimensions, and those dimensions are spatial. Okay, so that's our conclusion. We can see it. We can see these extra dimensions, and that they are indeed three spatial dimensions. This notion that the eyes can be used as an instrument, it's something that we see throughout literature and psychology. I'll just make a couple notes here. This fellow, Peter Michelson, he's a depth psychologist, very popular fellow. He wrote an article called When Eyes Are Blinders of the Soul. We don't have to worry so much about the word soul here, but he advises that people aren't really able to see the world unless they developed what he called a reflective life. And that reflective life, he says, is which sees from the depths behind our eyes. You get a notion that you're seeing from behind your eyes and using the eyes to see the world. I always go back to William Blake. In Songs of Innocence, he had this classic line. It's quoted always, and here's the line. I like it a lot. This life's dim window of the soul distorts the heavens from pole to pole and leads you to believe in a lie when you see with, not through the eyes. So again, Blake and Michelson are saying you look through the eyes from a place behind the eyes that has been called the watcher. I have skipped 30 pages of research from philosophy and science around the world about sort of substantiating these notions about the migrating self through the three centers and the kind of world that is seen from these various locations. And in the end, we come up with these three mnemonics. And I've tried to do mnemonics throughout the book to help people, and memory, little memory, as we call today, hacks, memory hacks. And here's they are. Here's the three. When the self is located in the head, we conceive the world, we think the world, and experience its objects as imbued with associations. We look at objects, what we experience is their names and the various memories that we have associated with them. We went a long time into the Japanese notions of using the path to a tea house to quiet the mind. We talked about Adam and how Adam named the animals and so forth. There's a lot of ways of looking at this that lets us come to this mnemonic conclusion. Okay, so that's the head. When the self is located in the heart, we taste the world. And I went into a long research about how taste and aesthetics came to be. We taste the world and experience its objects imbued with aesthetics. That means we see the world in terms of color. We see the world in terms of shape and in terms of light. Okay, now here's one more. When the self is located in the stomach, we will the world, and we experience its objects as imbued with dynamics about force and movement and speed. These are three, what we call three spatial dimensions. For instance, what I'm saying, what we're saying here is it's not so radical, it's not so rarefied and so forth. Just think of use this example in the book, just think of a group of people standing looking at the American flag while it's furling in the wind. Certain people, when they look at it from their head, the people who are looking at the flag from their head, they will see the concepts of the flag, the symbols of the flag, the loyalty to the president, the history of the stars, the founding fathers, and so forth. Someone is looking at the flag using your eyes from the area of the chest, looking at the flag, will see the colors, the red, white, and blue, the relationship of the stars, the light coming through the flag from behind or something like that. Those people who are looking at the flag from the stomach, using the eyes from the stomach, will see the dynamics of the flag, the motion of the flag as it's moving in the wind, or the bending of the pole, or the flapping of the rope, or so forth. It's not such a leap to see that people, to understand that people are seeing the world in different ways. The leap is to go into the spatial consequence of that and to say that each one of these people are actually perceiving a different dimension. Interesting. I find it's very fascinating what we did there. And just to help people with that leap, the hard part is to say, okay, some of us see color, some of us see symbols, and some of us see motion, but how are those dimensions? Why do you say those are dimensions? That's the leap. Mm-hmm. Something like your leap of you don't need to see. Right. That leap in the realms is that this can solve problems. You don't need to visualize it. Right. Now, that is the thing that's sort of hard to understand about realms. And one of the things that's hard to understand about these different dimensions according to how you're using your eyes is say, well, how are those dimensions? Well, one of the things that we did in trying to explain the notion of that these perceptions are different dimensions is to look and see, well, how do the pops describe and validate that something is a dimension? When the pops, this is all over the place in popular science books, right? The question becomes, well, what is a dimension? And I'll say, well, it's a coordinate. One of the things they say is it's a coordinate, okay? Another thing is they say that it is observable. So spatial dimensions are observable. And everyone says that you can't see 10 dimensions, you can only see 3. We went into that a long time ago, last session. So how do you know it's a spatial dimension? It's observable. It's described and can be used as a coordinate. I'll explain that one in a second. And there's also this notion that I tagged the term crossover. There are crossovers between the dimensions. And as an example of that, for instance, you could say that in the 5th, 6th, 7th dimension or so forth, the strings in those dimensions, when they appear in the 3-dimensional world, will appear as particles. That's the crossover. So what is seen as one aspect is a certain quality in one dimension will be seen as a different quality in the other dimension, okay? I said, okay, well, can we apply these 3 criteria to our proposed dimensions? And in fact, we can. They are observable, which is our basic notion. I won't be talking so much about crossover here, but I can explain that if we need be. I'm going to look at more the aspect of coordinates. Now, coordinates is often explained by, let's say that 2 people want to get together. They're going to get together at the corner of such and such street on such a floor at such and such a time. That was the X, Y, Z, and time. They add the time dimension. So let's take a look just for one quick moment about what we're talking about, our dimensions according to how you're using the eyes. Let's say that 2 friends are getting together, and they are at the time of their time of their getting together and talking about their later meeting, they are residing in their head. Okay, and so what they say is, now we took this example. I use the American flag, so this example I'm using from Toronto, the CN Tower in Toronto. They'll say they're going to meet at the corner of Front Street West and John Street on the glass floor level at 2 p.m. on Tuesday. So they agree, they're residing in their head, and they're going to meet within these 4-dimensional coordinates with height and time. However, these 2 people have read our book, and they also know that when they come together, they may be residing in their heart, or they may be residing in their stomach. And so they make 2 more agreements that allow them to meet and coordinate. They may be in one of these more what we call rarefied stages when they meet. And so they go further and they say that they will also meet at 1500 lumens of light. That is an aesthetic parameter. And they'll meet at 4 feet per second of speed. That is a parameter of dynamics or forces, objects moving at a certain speed because of forces. Now, when our friends come into the glass floor level at the right time, on the right day, in the right building, and so forth,
physically they're going to be the same spot.
Physically, they're in the same spot because 3 dimensions, the 3 physical dimensions don't disappear. However, one of the friends, in coming into the coming to the meeting, is perceiving the space using the eyes from the stomach, perceiving the space from a dynamics point of view. So that to that person, the group of people on the glass floor level will appear as objects moving about, as either by force of electric wheelchair or by force of their muscles and so forth, that they will perceive the space as filled with moving objects. But the other friend, if the other friend comes and perceives, is using the eyes from the point of view of the heart, will see the objects of the room in terms of their color, in terms of their shape, in terms of the light that they are exuding. Our friends who had decided to meet would in fact not be able to recognize each other. And this is something I'm afraid we would need to talk about quite a bit at a time. But if you are relating to the world from the viewpoint of the heart, the mental capacities of the head using the eyes have quieted down, and so you can't think. You have no thoughts. You're approaching the world only through aesthetics and light. And therefore, you wouldn't be able to say, well, who was that person and how do I know them at work? All that conceptual notions would be gone. These two friends who had decided to meet with each other, because they came into the space perceiving from a different location in the self, using the eyes from a different location in the self, they will in fact not meet. Mm-hmm. They will pass as they say, as ships in the night. They will not see each other because they will be experiencing the space as a different dimension. Okay. So that's the coordinating part, and it means I think that we answer quite well. We answer quite well the Pop's demand for the three kinds of criteria used to determine whether things are a space. Mm-hmm. One is observability, one is coordination, and one is crossover. So I think this is another place where I feel that the popularizers of science would be better scientists if they would accept, at least look with serious intent upon these different modes of using the eyes and space, that is the two extra dimensions, the dimension of the stomach and dimension of the heart. That would be aesthetics and dynamics. And that they would be better scientists were they to do that. I want to just say one thing before, since in fact this is our last podcast about our book and so forth. I just wanted to say that there's a large coordinated pattern of concepts that comes about in this section that we aren't talking about. But this has been called the kenosis of self. That means the self, as you sink down through the body, becomes more and more rare, more rarefied, becomes less and less substantial. Sinking out of the head, thoughts stop. Thinking out of the heart, the aesthetics stop, and you're left with dynamics. Sinking out of the stomach into what we might call lower realms takes you beyond the realm of dimensions completely. And that is where nothing resides. As we've titled our book, Nothing and Nothingness, we're never far from the value of nothing or nothingness helping us interpret. So when you think about this verticality of the selfhood using the eyes, at the bottom there, at the what we call over the cliff edge or beyond the continuum of selfhood lies nothing. Right. And it is the basis for which we can use to find these interpretive tools. Just one last thing is that we have a kind of motto for the book, and it says that nothing makes the world real and nothing makes the world work. So in this case, nothing helps us see the reality of these dimensions, and nothing helps us come up with this interpretive device that helps us create this notion of dimensions and location of self.
So by sort of being able to see through the eyes instead of seeing with them, right? Seeing through them via the mind, seeing through the eyes via the heart and the stomach. It's like having that experience, knowing what that's like, and sinking lower and lower, right? Accepting to turn that part of that seeing off, to actually close your eyes, right? You can only close those eyes once you're aware you've had them open to begin with, right? You need to have had them open to begin with to be able to close them. And in so doing, right, you are allowing yourself to sink lower and lower towards this nothing, right? The base of it all, the substrate of objects and subjects. And to this point, this is not, I mean, these two ideas, these two ways of understanding sort of higher dimensions are related. I see, you know, it's, yes. If I understand you correctly, right, this is, your dimensions are a way of seeing, essentially, as again through the eyes, not with them, right? Having that watcher sort of behind the eye. That's where the self is located. In a sense, Relms is like seeing the dimensions through the gut. You feel your movement through space, and you're replacing this motion of particles with your own motion, which you experience now no longer through your eyes, right? But you experience it through your gut. You feel that sinking feeling, right? That acceleration through space. You, in fact, are moving, right? And it's not the particles that appear to be moving.
Right. I had never heard you say that, the gut feeling, before, but I noticed that and saw it.
But you get the idea of the gut. Like, we have that very real experience of that gut feeling. We're in a car, or we feel those G-forces on accelerating, like upon takeoff. We know we're moving, and it's our gut that tells us that. Because being in that chair, on like as we're about to take off, the windows are closed, right? So we can't see like from our vantage point, everything's static. What gives us the sense that we're moving is that feeling of acceleration, that feeling like that being thrown back into our seat.
That's right.
It's certainly not the motion of our surroundings that's telling us that. So in a way, that's how we have a sense of that, seeing through the gut, or experiencing the world through the gut, right? So let's advise the scientists to take that a little bit more, look into that a little bit more, and maybe not be so focused on the motion of these objects. Sometimes maybe gestalt and think, well, maybe we're moving. We're a part of this dynamic. We're a part of what's going on in front of us.
Yeah.
That's all I got for now. I think I'll wish you and your loved ones a very happy holiday.
Oh, yeah. And you.
And it's been a wonderful experience doing this with you.
Well, thank you too. I appreciate it. See you next time.
See you next time. Bye-bye.
Entering the Universe has been brought to you by the Society of Namecoin. Until next time. No.